In this video, I will go over prime numbers, composite numbers, divisibility, and prime factorization. The goal of going over these items is to allow whoever is learning these concepts to be a little bit better at doing fractions, because these are kind of the foundations towards fractions. So let's begin with prime numbers. Now you may recall that natural numbers were made up of all our counting numbers, 1, 2, 3, and so on. So all are positives. Now, this is a set of numbers, and prime numbers are a subset of these natural numbers. And in particular, we define prime numbers as any natural number that is only divisible by 1 and itself. And this subset of the natural numbers, by definition, is the following: number 2, 3, 5, 7, 11, 13, 17, 19, and it goes on forever. Why are these numbers prime? Meaning, why are they only divisible by 1 in itself? First, you will notice that the number 1 is not in this set, and that is just by definition. Prime numbers skip the number 1. Now, if you look at the number 2, well, there is no other natural number that will go into 2, because obviously it is the smallest one. Anything bigger that you will try to bring and divide it into 2 will cause you to create a decimal. So number 2 is our first prime number. Number 3, again, is only divisible by 1 and itself, 3. Now, as you're going through this list, the only numbers that you really have to check are the primes that come before it. So for instance, the number 5, you can check, will the number 2 go into 5? It will, but it will leave us a remainder. And if it leaves us a remainder, then it does not divide into 5 equally. Number 3, it's the same problem. It will go into 5, but again, it will leave us a remainder. So therefore, that turns out that 5 is prime. Same thing happens with the number 7. So you can check if 2 or 3 or 5 will go into 7 evenly, and it will not. Same thing happens with 11, 13, 17, 19, and so on. Meaning that these prime numbers are only divisible by the number 1 and itself. And the key thing is that it has to divide evenly. There cannot be no remainders. So that is the set of prime numbers. Now, if you look at the set of natural numbers above, clearly we have skipped some numbers. So for instance, let us take a look. Which ones did we skip? Well, we skipped 1 by definition, but then the next one is the number 4. Now 4 was not prime because 2 would go into 4 evenly 2 times. Next one is 6. 6 again is not prime because 2, or actually 3, would go into it evenly. 8, same problem. 2 will go into 8, so 8 cannot be prime. 9, 2 will not go into 9, but 3 does. Therefore, 9 cannot be prime because there is another number that goes into it. And you can do this for 10, 12, and so on. And again, this set, which I'm putting in brace brackets here, is the set of all our composite numbers. Meaning, it is the set of all numbers that are natural, but that can be divided by some prime. And if you combine these two sets, so if we would bring these two sets together, so we would create a union of these two sets, bringing them together, you will notice that we will get the natural numbers back, and then we would put the number 1 back into it. So those are prime numbers and composite numbers. Now, this set of prime numbers is important because every natural number can be written out as a factorization of primes, and you will see that shortly. Now, I mentioned this term here, which is divisible. So it's a nice term to take a look at, divisibility, that is. So let's see what this divisibility is all about. So what I want to concentrate on is divisibility by particular numbers, by the prime number 2, prime number 3, prime number 5, which are the first 3 primes, and then the composite number 10. Now 10 is simply 2 multiplied by 5. So what I want to do now is know if someone gives me a number, any number at all, can I very quickly check if that number, the natural number that is divisible by any of these. For example, if I would give you the number 16, you could very quickly tell me, oh, I know that 16 is divisible by 2. That's what we mean by divisibility, meaning will a number be able to go into another number an even number of times? There are actually pretty nice rules for these set of numbers, 2, 3, 5, and 10. Let's take a look at them. Turns out that for the number 2, a number is divisible by 2 if and only if it is an even number. Now, what does it mean to be an even number? It means that the number ends in the digit 0, 2, 4, 6, or 8. That is why 16, because it ended in 6, was divisible by 2. And this works for very big numbers. We can arbitrarily write a number like this and very quickly check. Well, it ends in a 7, which is odd. Therefore, it will not be divisible by 2. So all you have to check is the last digit and see if it is an even number. Now, the number 3 also has a very interesting rule. It is not as easy as with number 2. However, it uses this one concept, which I just want to let you know about. Now, divisibility by 3. So divisibility by 3 isn't as easy as just checking the last digit. You actually have to do a little bit of work, and it is related to the sum of digits. Sum of digits. And what I mean by the sum of digits is that if you have a given number, let's say 145, the sum of digits is simply adding up the digits. So in this case, 1 plus 4 plus 5. So the sum of digits would be 10. And if you want to know if this original number is divisible by 3, you only have to check if the sum of digits is divisible by 3. Now, in this case, we cannot divide 10 by 3, which means 145 is also not divisible by 3. Now, we can take also the previous example, so 2787, which is right above us. And now, if we wanted to check if this is divisible by 3, again, we just have to check the sum of digits. So we can add these up. So 2 plus 7 is 9. 9 plus 8 is 17. 17 plus 7 is 24. And now if we check if this is divisible by 3, then we find out that, well, 24 indeed is divisible by 3. Now notice you can also check this sum of digits. 2 plus 4 is equal to 6, and clearly it's divisible by 3. So that's a very nice trick that we have for divisibility and checking. So all you have to check is if the sum of digits is divisible by 3, then so is the original answer. When I scroll back here, the next item or digit was divisibility by 5. This one is very similar to divisibility by 2, where you can check if a number is divisible by 5 if it ends in a 0 or a 5. And it doesn't matter how big the number is. I can write a monstrous number here, and all I have to check is the last digit to see if that entire number is divisible by 5. And it is divisible by 5 if it ends in a 0 or a 5. So in this case, this number is divisible by 5. But if I would change this, now the last digit is a 4. Therefore, the number is not divisible by 5. The last case, divisibility by 10, is even easier because here all we have to check is if the last digit is a 0. And if it is a 0, then the number is divisible by 10. If it is not a 0, then it is not divisible by 10. So this helps us because when we will want to break down a bigger number into primes, we can use these divisibility tests to see how to break the number down. Which brings me to the last topic of this video, and that is prime factorization. So the word prime I have discussed in this video. So those are the prime numbers, and factorization is what will now follow. So I want to give you several examples. So here are some examples. Here's an example: 75, 66, 450, and let's say the last one is 221. And now what we want to do is we want to break these numbers down so that they're only made up of multiplication of primes. So let's see this by example. The first one, 75. I will on the side here write for myself the primes. 2, 3, 5, 7, 11, 13, 17, okay, and it goes on. Now, when I look at 75, from the previous explanation of divisibility, I notice that it ends in a 5, which means that I can divide 75 by 5. Now, how many times does 5 go into 75? So I can do that. So 5 into 7 goes once. 5 into 25 goes 5 times. Which means this is 5 times 15. Now, the number 5 is a factor of 75. The number 15, now I want to ask, can I break this down any further in terms of primes? And again, it ends in a 5. So I know that 5 once again will go into 15. So I have my original 5, now times, well, 15 is just 3 times 5. And notice what you've created now, every number is prime. Now they can repeat, of course, but when you multiply 5 times 3 times 5, you'll get 75 back. This is called the prime factorization because it is made up of primes and each prime is a factor of 75. The order, the way we write this, does not matter, and most of the time in math we try to write the smaller primes first and our larger primes afterwards. That's our first prime factorization of 75. Now what about 66? So for 66, again, I will look at my primes and see which ones go in. From the divisibility, I can see because it is even, I right away know that 2 will go into 66. How many times? So 2 will go into 66, and you can check this for yourself, 33 times. So this is my first prime factor. Now 33, I can break down further. 2 will no longer fit into 33 because it ends in a 3. However, notice that 33 is divisible by 3, which means I can now break down this original 66 into 2 times 3 times 11. 11 is a prime, so I cannot break this down any further, which means I have now created the prime factorization of 66. And notice all you have to check is primes, because all the composite numbers that we talked about are made up of primes. That is example number 2. Let's try a bigger example with 450. Now with 450, the first thing that I notice, because of our divisibility test for 10, notice that it ends in a 0, which means 450 is divisible by 10. Well, 10 goes into 450 45 times, and you can check that. Now, having these, well, I know that 10 is nothing else but 2 times 5, because remember, I want to have just primes. And 45, notice it ends in a 5, so that is 5 times 9. Now you might be tempted to say that you're finished. 2 is prime, 5 is prime, 5 is prime, but 9 is not prime. 9 is 3 times 3. So the full prime factorization of 450, and I'll write these from smallest to largest, is 2 times 3 times 3 times 5 times 5 times 9. I apologize. This now becomes our prime factorization. And if you multiplied all of these numbers, you would get 450 back. The last example, 221. So let's take a look and see what this gives us. Now, I noticed that 221, so it's not divisible by 2 because it ends in 1. Let me check if it's divisible by 3 by doing the sum of digits. If I do sum of digits, I'll get 5, which unfortunately is not divisible by 3. So 3 does not work. Let me check the next one, which is 5. And notice I am going in order if I do not see right away if something divides into 221. So 5 will not work because it ends in 1. Now 7. Unfortunately, there isn't a nice divisibility test for 7, so I will have to do the division to check if 7 goes into 221. So 7 goes into 22 3 times. That's 21. 7 does not go into 11, or it goes in once, but that will leave me a remainder. So 7 also will not work. So far, 2 doesn't work, 3 doesn't work, 5 doesn't work, 7 doesn't work. And I'm only checking primes. And this may happen. It's not always as nice as in the previous examples. Sometimes you have to grind away through the primes one by one to see. The next prime is 11. So let's check. Does 11 go into 221. So 11 goes into 22 two times. But that will bring me a 1. And unfortunately, 11 does not go into 1. Well, it goes 0 times. So I'm stuck with a remainder. So 11 also does not work. Next prime is 13. And now 13, you can check for yourself that 13 will actually go into 221 17 times. And that means that it's 13 times 17 gives me 221. 13 is a prime, and 17 is also a prime. And that becomes the prime factorization of 221. I cannot break this down any further because both factors, 13 and 17, are prime. This concludes this video, and what we have gone through is prime numbers, composite numbers, divisibility, and prime factorization, which, as I say, is the foundation of knowing later on how to do fractions in a little better way. Thank you for watching.